But in your unknown samples, you don't know if that's the case. But you're assuming that this relationship holds to your samples, to the relationship that's in your samples, but it may not because of the presence of those other interference. Right? And the matrix is different. So when you perform a method of addition, your goal there is to essentially create a standard curve in your sample matrix. That's the purpose. And then you say, if there's stuff in there, and I don't know what it is, and I don't really care, but if there's stuff in there that affects this relationship between concentration and absorbance, then by mixing standards in my sample, then that matrix will interfere with my standards, and it'll change that relationship, and it'll be like, and that's okay, because now I can use that method of addition approach to determine what the concentration is in that sample. And so I can account for those matrices, right? And so matrix interferences are a common problem. And so you'd say, I've got the method, I can do this. And I'd say, that's great. And I'd say, here are 500 samples from water samples from around the state of California that you should analyze for these 10 elements. And you'd be like, all right, well, so that's 500, and I've got to do 4 addition points, so that's 2,000 samples, and I've got to do that for 10 elements or whatever, so that's like the rest of your life, right? And say, that's a lot of work. You'd say, well, is there a better way to do that, and a more efficient way to do that? And the answer is yes. You'd say, well, I don't know what the levels are, maybe they're low, but I can dilute the samples and the matrix problem out, and I can use a more sensitive instrument, and I can use some other approaches to minimize those matrix issues. And one of those approaches, this is what I'm kind of focused on, is by using other kinds of compounds that you can add to the sample. They call those matrix modifiers, in order to change the composition of the sample to help remove the effects that these matrix issues are having on the sample. And I'll talk about this before I do it. One example where that has become a standard is for all the clinical laboratories in the country that measure metals in blood, which is a common clinical outcome. And one of the ones that they measure commonly is lead in blood. We talked a little bit about lead, measuring lead by point they named. And so a number of years ago, there was a national policy to measure the level of lead in blood of every child below the age of 6 at least once. It was a screening program. I don't know how many kids are in the United States, but there are a lot of kids, right? And the policy was every kid had to have their blood lead measured at least once. And so it was a challenge analytically in the beginning because they had to actually do this in blood samples, because you can't hardly imagine a more complex matrix than a blood sample because it's got so much stuff in it, right? And so they had to take a blood sample and do a method of addition in every blood sample to get an accurate level to lead level in the blood. And it was a problem because it was a huge analytical undertaking. And so they developed analytical approaches using matrix modifiers where they could add chemicals like magnesium nitrate or ammonium phosphate and add that to the blood sample. And the magnesium nitrate and ammonium phosphate would complex with the lead in the blood, and you'd add it in excess so that rather than the lead being bound to the proteins and the other things in the blood are going to affect how it volatilizes and atomizes, all the lead gets converted to one of the salts, phosphate and nitrate. And it takes an analyte that exists in many different species or forms, kinds of complexes in a complex sample like blood, and it essentially collects all the lead and puts it in some very simple inorganic species. And it made the behavior of the lead in the blood sample much more predictable. And it removed, and it made it more predictable, more stable, and they were able to remove the interferences from all the proteins and things in the blood by doing that. So it allowed them now to screen every kid because they could make a blood measurement very quickly. And so I'll show you quickly how that works. So this is an example of, say, stick that analysis of blood. This is an example of what an analysis program would be like in a graphic furnace atomic absorbance instrument, where you would inject the sample in a blood sample, and then you would heat it up, and you'd get a bit of absorbance because you got the water vapor coming off. And then you'd raise the temperature to break down the organic matter, and you get all this organic matter in the blood, generating all this smoke that would be absorbing non-atomically, absorbing all this light, you measure that as absorbance. And then you get to the atomizing step where you volatilize your lead, in this example, let's say, and you get a lead absorbance signal there, but it's hugely interfered by all this other stuff that's also burning off during that step. And so by adding a matrix modifier into the sample, mixing it with your little sample before you do the analyses, then you can actually raise the temperature at which you're charring or trying to break in the organics compared to this temperature here, right? You can raise that temperature, burn off all the organics before you can make a measurement, so that when you do finally make the measurement in the atomization state, you've removed all the interferences from the organics. And that's commonly what's done. Right? So you would take a sample and you would mix in matrix modifiers, and if you were doing like lead, and if the instrument gets repaired and you do lead in some samples, you would be using a matrix modifier in order to sort of separate those interferences from the lead signal and be able to make those measurements without those interferences. And this is kind of an example of the challenge you're facing. Is ideally, when you have a sample, and this would be like during a normal cycle where you're reading it, let's say this is where the temperature now gets up to 2,500 degrees C. And this would be like a 5-second duration. When the temperature spikes up to that temperature, the analyte, say the lead in your sample, would volatilize and atomize up in the gas stage, and you'd start measuring the absorbance of that. And you would measure the absorbance over this entire 5-second read period, and you'd integrate that signal just like you do in the IC measurement. And ideally what you'd want is you want no background there, so the background or the baseline would look kind of flat like it was up there. Because then you can integrate that signal, and that would represent the total amount of lead, in this example, that volatilized that you're measuring. If the instrument's not stable, or the baseline's not stable, it might give us a slanted baseline. We've seen that problem with the IC, right? And you were able to deal with it, right? But more commonly in atomic absorption, you do have a relatively flat baseline, but you have the presence of other non-atomic absorbance that it's actually being measured. And that would be the example I showed right there that would be interfering with your analyte. And so to account for that, one is we can add components to samples to change the chemical composition of our analyte so it behaves in a different way. So we can separate it from interferences. Or we can use, aspects of the instruments that perform some background correction or background measurements of absorbance that's not attributed to atomic absorbance, but in fact is attributed to non-atomic. And so many instruments, not yours, but many more expensive instruments, have the means to measure absorbance that attributes to the atomic absorption signal that we want, and have the means to measure absorbance that's being attributed to a non-atomic absorbance signal, which is the background, and to subtract those two to determine how much is really atomic absorbance. And so you can look at this in a perfect world. This sort of applies to UV-Vis spectroscopy in some ways. What this is meant to show is that normally you start by saying, in atomic absorbance, I generate an atomic spectra that's very defined from my Howell cathode lamp, let's say. And I'm going to be measuring within a very defined window of wavelength. I'm going to be measuring absorbance there. So I generate this atomic spectra, but I'm going to be measuring only one wavelength, 324.8 nanometers, let's say, for copper. And then when I look at the absorption spectra, the copper atoms in my sample, maybe it's a little bit broader for a number of reasons we've talked about. And then I'm going to look at the absorbance of that source line by the atoms of my sample, and I'm going to measure the difference. That's going to tell me how much was absorbed, how many of those photons were absorbed, and I can calculate my standards, convert that absorbance, relative absorbance, to a concentration, right? If I start with my source emission spectra line, this is the atoms that are in my copper in my sample that are absorbing that light, and the difference is how much gets through the detector, and that's how much was absorbed. And I can calculate easily what's there by then. But in the case of atomic absorption, we know, and I pointed out, that we don't use a deuterium arc lamp or a broadband emission source to generate light because the light is too broad and spread across a wide range of wavelengths, right? And so we don't use deuterium arc lights to generate a source of emission, a source of radiation that's going to be absorbed, but we can use the deuterium arc lights, lamps, to generate a broadband radiation that can allow us to measure background absorbance and as a way to try to correct for the non-atomic absorbance. And this is just meant to kind of show that. So if you look at the top, this is normally what we were dealing with in UV-Vis spectroscopy. is that we generate light from our D2 lamp, and it has a relatively wide bandwidth of say, a nanometer in this example. Right? And so you know you have a peak absorption maximum at 482, and we're able to select for light around 482 nanometers with a monochromator and UV vis. It's maybe 482 plus or minus a half a nanometer, right? So it's relatively broad. And then our molecular species is absorbing across a broad band. You do that wavelength scan, it looks like that. And when we then look for the absorbance of that signal, it's being absorbed by our molecular species, we can actually compare the absorbance and get a pretty good signal, a pretty good measure of the intensity of the incident light versus the light that comes out to determine absorbance, right? And we have those broad bands. That works fine in this spectroscopy. If you try to apply that same concept to atomic absorption spectroscopy, where you started with a broadband source spectra like this, 1 nanometers, and we have our atomic spectra of absorbing a copper that's absorbed at a very specific line, we would see that if this was the band of wavelength of light that we were using to pass through our sample, and if our sample is only absorbing at a very narrow band of wavelengths, when we were trying to look at the amount of light that we pass in versus what comes out and how much is absorbed, we'd be looking at a very small slice of the light we pass in is actually absorbed, only a very small slice is actually absorbed by our copper atoms in this example, or whatever, right? And so the point here is to say that for UV vis, where we have broad absorption bands of our complex, copper complex, then we can use a broad emission spectra light to evaluate or to measure absorbance by that complex. If what's absorbing does not absorb in a broadband absorbance profile like our complex, but instead absorbs at a very sharp atomic line, then we can't use a broadband spectrum pathway. But if we have non-atomic absorbance that typically manifests across a wide range of wavelengths, it turns out that this broadband emission source is actually perfect for measuring that non-atomic absorbance because it comes in a much broader range of wavelengths, and we're able to use it quite effectively to do that. Let me say quickly how that's done. So I'm going to skip this because we don't have time to go right to the next slide on that. Let's draw this up. Should show right there. Okay, so this is our atomic absorbance line that we do measure in the sample, and if we're monitoring, if we're monitoring absorbance over a range of wavelengths, in most cases, certainly in the case of the flame atomic absorption, we would also see this non-atomic absorbance. If we had the means to, which we're not measuring that. So right now, you're measuring absorbance right in this window with the instrument. The monochromator is narrowing and only allowing wavelengths of light in this relatively narrow band to strike the detector. Right? And in your instrument, you are in real time measuring how much of the absorbance, when I'm looking at the light that's coming out, the incidence light, and the light that's actually striking the detector, I'm comparing those two to measure the actual absorbance, just the same way. How is it in this case that if you're doing that, in your case, how is it that you might be able to correct for non-atomic absorbance that happens to pass that same band of wavelengths, or that same wavelength band? Is there any way that you could do that?
Split the lines up on either side of the...
So you're measuring everything inside of here.
Can you raise the line from that?
Background one.
Background, yeah.
Well, this is, if I could measure separately absorbance due to atomic absorbance and absorbance due to non-atomic absorbance, then I would get two different lines, right?
Right.
In your instrument, you can't do that. In your instrument, what you're measuring is total absorbance in this wavelength window. So you're selecting 324.8 nanometers, and the bandwidth of that absorbent peak is probably about 0.1 or 0.05 nanometers. So you're probably measuring between 7 or 6 or 7 and 324.9, and you're measuring all the absorbance that's occurring within that bandwidth of wavelength.
Since the peaks are theoretically at least a Gaussian curve, you could measure the absorbance at like 1 or 2 standard deviations away from the center, and then that would...
If you could measure that finely, if you could parse that out and measure at intervals of 0.01 or 0.001 nanometers, you might be able to do that. And you sort of define that, you can't, but you don't, monochromators aren't that effective.
Isn't this why we don't have definitions?
So well, this is why you're doing about definition. That's right. Because you know there may be something there that's interfering, but I don't know what it is, right? But all the absorbance I'm measuring is the total absorbance of all that. But I'm saying analytically, because method of addition is a lot of work, analytically there's a way that we can get around that. And not in your instrument, because your instrument doesn't have any means to actually measure separately atomic and non-atomic absorbance. But most instruments do. And what most instruments do is they'll use some other broadband light source, like a deuterium arc lamp for atomic absorbance. And they will have a setup where they have a hollow cathode that's generating the atomic emission you want. And they'll use like a deuterium arc lamp that generates broadband radiation, electromagnetic radiation, across a wide range of wavelengths. And they'll incorporate, in this cartoon, they show a mirrored chopper. What that essentially is like a fan. It has a polished mirrored surface that rotates, and it rotates at a certain speed. And when it rotates, it either is letting just a hollow cathode lamp go through, right? And then, so you should be measuring all this. So that would be atomic absorption plus, I'll call it background, right? So the HCl lamp is measuring that. And then it would, when the mirror is rotating, then it would block the hollow cathode lamp and reflect in light from the deuterium arc lamp to pass through the flame, in your case the instrument. And then it would be measuring only background, right? So the D2, the deuterium arc lamp will be measuring only the background signal. A hollow cathode, when that's going through the sample, will be measuring atomic and background signal. And then the instrument is actually two subtractors. So when just the D2 is going through, it's just measuring this part. When the A is going through, it's measuring all this. And by subtracting the 2, it's actually able to get a measure of what is truly, they think, is atomic absorption, separate of the atomic, separate of the background. But your instrument doesn't have that on it because it costs more money.
Wouldn't the D2 arc lamp also capture some of the NR?
It does. But for this reason here, it wasn't that obvious, the amount of absorbance of this broadband radiation from the D2 that is being absorbed by the copper, the very narrow atomic line, is extremely small. So it's no good for measuring atomic absorption, but it's perfect for measuring non-broadband, non-atomic absorption without being significantly interfered by absorbance from the additive side. From the atomic absorption itself. All right, so I didn't get nearly as far as I wanted to get. So I'll finish talking about this next Wednesday briefly. One thing I wanted to throw out, probably 3 or 4 or 5 years ago, one of the labs we actually did in this class that we made, bro, and thought that it didn't be too complicated, was this, where we we're interested in, we just made this up, say if we have arsenic in water, and arsenic in groundwater, drinking water is a huge environmental health problem in many countries in the world. We developed a method that allows us to look at the arsenic species, whether it's arsenic 3 or arsenic 5, or whether versus total arsenic, and measure those in water samples. And there's a reason we want to do this in terms of environmental health context, because arsenic is so toxic. But like a lot of metals in the environment, the species of the metal, and that means the form that it's in. The species is something that we use to characterize both the oxidation state and the molecular form that it's in. Sort of belongs together. The species of arsenic is in the environment determines its toxicity and how geochemically transformed in the environment. And so normally it's arsenic 5, arsenic, and because it's an oxidizing environment, when it gets reduced to arsenic 3. When people drink it, it gets metabolized into monomethyl arsenic, and finally into dimethyl arsenic over here. And these organospecies of arsenic are what the toxic forms are. And so there was rationale to want to do this, and there's a method. Look at all this stuff. There's a method that utilizes sort of a reduction of arsenic in formula of a color-absorbing, light-absorbing complex. It can be measured by UV vis spectroscopy. And then we combine that method with ion exchange, a desktop ion exchange, not the IC which we use. With a desktop, meaning a little column on a countertop, ion exchange that allowed us to separate the different inorganic forms of arsenic that we could measure by flame AA. And so by combining the method, UV vis spectroscopy, and a flame atomic absorption spectroscopy, it was possible to measure the different species of arsenic in water samples and make inferences about the relative risk. Right? Now, there's nowhere here in our environment you could easily go and collect samples that have very high arsenic levels, because you don't have that problem there. But there are plenty of places elsewhere to do it. And so I posted this on the website as an example of a method that could be used to do something like this. And in this case, this method uses two of the methods that we use in class: atomic absorption spectroscopy and ion exchange chromatography, in order to get at a question of how the species, in this example, how the species of arsenic is changing depending on the water, the chemistry of the water, or where the water samples are from, or something. And so when you go through and start thinking about what you want to do for your lab 4, there's a whole range of obviously possibilities, and sometimes the infinite range of possibilities can be daunting for people because it's hard to select something. Right? And so I would, one, is try to think of something that's of interest to you personally, and where somebody would care about it, because underlying all scientific experiments, hopefully this would be the need to want to know the answer, and it's an answer worth knowing. And so even if it's only worth knowing to you, that's okay. It has to be something that you're interested in. Right? And then if that's the case, then the next challenge is only whether it's feasible or not, what we have available to us.
Does it have to be like measuring something from water samples, or can we use something different than just water samples?
In the past, last year, some students asked the question, how much zinc and iron is in a turkey dinner, because it was Thanksgiving time, and they collected samples of Thanksgiving dinner and digested, homogenized and digested it, and it was kind of a mess, but that's what they did. Other people in the past have asked, what's the difference between the anion content of the various power drinks on the market and Gatorade and whatever they all are. And they analyze those by chromatography. Other people, I tell you, the one thing you cannot do is you cannot do anything that requires collection of a sample from a human being, unless it's urine, but you can't do anything invasive, so you can't get blood. Right?
Hair follicles?
What?
Hair follicles?
Hair, you do hair, anything that's non-invasive, that doesn't require human subjects' approval from IRB. You can't do anything that involves animals, right? Unless it's non-invasive collection of something. You can't do anything that has, a huge toxic risk, health risk, let's use it obvious. But otherwise, it's like, no, it doesn't have to be water, it could be anything you want. So if you want to digest biological samples, like hair, people did that, right? And then ask questions about it, what's the content of blah, blah, blah hair from different people, whether based on what hair products they use or whatever, you know, that's totally doable. Right? It requires a lot more work than what you, in terms of the processing, than what we experience, but we can help prepare for that. Okay, so I'm gonna stop. So we're gonna meet in
1 o'clock?
1 o'clock. How many people are you? Want to try to come by at 1? Okay.
Can I come at 3?